require size different than 0 is true, no problem, no warning. So we cannot find this kind of bug by our tool. And like this can happen, like you can have an index, for example, where the index is going, in that particular case, you allocated the size plus 2, but then you will say, because you have a memory copy just behind that is just used on the size read from the network, and not size plus 2, 0 bytes are copied, which is not buggy, everything is fine, like memory copy of 0 bytes is fine. And then the counter that is holding the number of bytes that were copied is 0 because you have copied 0. And then you pass like that, exactly in the case of the allocation, except that you have allocated 0 plus 2. You have some kind of pointer that was allocated with 2 bytes, whose data is uninitialized and passed to internal API. So you do that, and what you realize is when you look a little deeper at the code, the first time you call the API, it's going to check for 0 correctly. So it says, oh, if this was 0, it's an error. This is like this stage is not valid, so return invalid, so incomplete packet. And if it was not 0, you actually allocate the final buffer where the data is going to be copied. And also you have the case where you send more than one time the data. So in that case, you do a realloc. So you're going to have a string where you do the copy of the string. The string is non-zero size, can be whatever you want. And then you send another string. So think of remote protocol. So like obviously, like I obfuscated kind of lots of details, but there are many of them are like that. And we do that, you have a mine field, and you have, if you put the mine field twice, then actually the two strings of, value strings of the mine field are going to be happened. There is like a concatenation of strings. The thing is, if the string was not empty, it's going to concatenate the string, but in that case, it doesn't check for the size 0. So the number of bytes that you had copied was 0, and then this is bad because you have decremented counter. So in the case where you send more than one field of the same type, you have first like a legit string, and then you concatenate the second string, which is this time a 0 string. So it was allocated with 2 bytes, but still it's concatenated with 0 bytes because as we saw, the initialization is done with only 0 bytes, not 0 plus 2. And you have a state variable that holds how many bytes were copied. And in that particular case, for the second string, this variable is 0. And then you do a decrementation because the first byte is something particular. So you just handle the first byte, say this is the type of the string, and then the string itself. So you expected the string to be at least 1 byte big, but in the case where you already had the type field, you were not checking by the size to be 0. So the first case you send the string, the check is well done. You say, oh, okay, if it was 0, invalid. But then if you send the other field a second time, it's not checking for the size to be 0. So you concatenate 2 strings, and the second is a 0 string, and then you have an integer underflow on the number of copied bytes. And so the number of copied bytes is becomes 0 minus minus, which is a very big number. And then you have a copy of memory on that. So you do a copy of a very big size, which leads to a heap overflow. So this example is just to say that S0 allocation is not like the ultimate property, because like in the neighborhood of that property, we have actually similar property that also brings us bug. And this, with the very simple check we have presented, the required size different than 0, we cannot find those because the size is not 0, it's 1 or 2 or 0 plus constant. So it's another kind of subclass of buffer overflow. Conclusion. So what we have tried is to approach automated detection of buffer overflows, which is a very complex problem. So in order to do that, we try to identify subclasses of buffer overflows that are generally more problematic for developers. So when we deal with boundary values, say 0 or FFFS, or like this kind of value, it's generally much more complicated for developers because they have to check everything, and like many of them don't. So by doing specific analysis on specific buffer size value, we can actually isolate bugs that are interested for us. Obviously, not all buffer overflows, but those buffer overflows that are specific to this subclass of buffer overflow. So we have reduced the problem space to those cases where the size is 0. You can also do that on other boundary values, like I just said. We didn't do it, but feel free. And report the bugs to us, please. And so this approach worked pretty well because for a million lines of code, you just have like around 100 warnings, and the rate of false positives is like very acceptable because just in like 2 or 3 days of review warnings, we can say either, okay, we have no bugs of such type in a million line of code, or all the bugs have been fixed. So this is a rather interesting approach. Not only we do that to find new bugs,